This is something we worked with for years and years, and these things, we're going to get away from them, and it's because of the computers again. This is how we used to live. Every time you ran a neutron density, you had to have one of these charts sitting right next to you to establish what the readings meant. And all they're showing is the different lithology, if you will, evaluation curves showing for dolomite, calcite, and sandstone. Depending upon what the two porosities were on the neutron density, what kind of lithology am I in, if you will. Or if you look off to the left, you see this approximate gas correction. That would be the direction you'd have to shift the points when you're looking at the log if there were gas in the formation. Now you can pick lots of different minerals and have different mineral points and tell what the lithology is based on these two curves. So typically, if you were interpreting one of these in the past, you'd have to have this sitting next to you at all times so that you can establish what these are. And once they introduced the PE curve, you had another chart. It becomes a little more complicated, but it's just a chart. Of course, what's happened with computers today is we've managed to throw this into, if you will, the digital world. You can input the values and it will give you a reproduction of this chart. But that's what you're working with. So you can imagine if you're working with these two charts, you can imagine what's happening time-wise. I'm starting to spend a lot of time now sitting down evaluating my logs, right? I'm spending a lot of time just to get to my basic answer that I want to start to work with. Now this is the response of the PE itself. It's kind of interesting, and the reason I put it up here is because you'll see the PE response as porosity changes. If you look at the block on the left, as porosity is going from 0, say, to 50% from the right to the left, you'll see what the PE response is for the different lithologies. When I don't have any porosity for a calcite, it's reading real close to 5. But what happens in that same calcite as porosity increases up to 35%? I start to have a window of values, right? So if I'm in water, for instance, in the formation, and my porosity is increasing, there's not a specific calibrated number that you're going to see. It's going to be a variety of values. If we're looking at calcite and we look over here, it's going to be varying from 4.23 to 4.96 for the same rock. Okay? So that's another thing that you need to be aware of when you're looking at the PE curve and trying to determine what the lithology is. Make sure you understand that response and that that's going on. Now, if the same formation has gas in it, you can see right off the bat that you don't have as much change. So the big change is occurring with what? Water in the formation. And when you're working with just pure quartz, over here, you don't have as much of the change. So these are just inherent things and the way the curve works that you need to have in the back of your mind all the time when you're looking at that. Next, we got the microlog. Well, what do we call the microlog? It's probably the first porosity device, right? It's been around for a long, long time. 60 years? 55 years? So we're going to call it the original porosity device, and it doesn't measure porosity, right? It's inferring it. But it's another resistivity tool, only it's a real finely spaced, closely spaced resistivity tool. We're talking about 1.5, 2 inch type curves. This is one curve. This is one of those logs that was heavily run in the beginning of logging. And then after about 30 years, it kind of went away for a while. You didn't see it very much. You'll see, if you look at the data, you'll see gaps when this was run and then when it wasn't. And then in the last 15 years, what's happened? It's come back. Because we found out the value is still there. We kind of lost it for a while. And now we're back, it's back in the fold. It's still the microlog. So the definition is still the same. And finally, the other common log that we have is the sonic log. And we're using it, if you can use it for what? Your seismic data? You can use it to determine what the sonic porosity is. Now what's the important part about having sonic porosity in the interpretation process? If we want to know what the secondary porosity is, which is extremely important in carbonates, you have to know what that sonic porosity was. Because if you take that total porosity that we measured, for instance, on a neutron density, we have to subtract out the sonic porosity. Well, there are a lot of cases where the secondary porosity is driving how good a well you have. What's the permeability in an open fracture? It's a big number. It's a really big number. So all the fluid can be producing through what? The secondary porosity portion of that rock. So if we don't have that number, if we don't have that value from the sonic porosity, we can't establish what this might be. So another basic concept, especially working with carbonates, another basic concept that we have to work with. Talked about the Archie equation. Will always look just like that, and I don't know that it'll ever get replaced. The other thing we have, and this has always been the bugaboo with dual induction logs or induction logs, induction electric logs in Kansas, is trying to establish what the resistivity value really is. What's the number? We talk about RT, the deep resistivity, RT. What's the number that I should be using? Can I just read it off the log? Well, in Kansas, probably no. We don't have zones that are thick enough. Anytime we're talking about induction type devices, they're reading, if you will, a cloud in the formation, and it's a pretty large cloud that it's reading. If you ever go out to if you can get to a district and watch them calibrate a dual induction tool, until that dual induction tool is removed, for instance, from the ground, until it's pulled up in the air at least 13 feet, it's reading the ground, okay? So it's reading this big cloud of resistivity surrounding it. Well, if you're doing that, then it's going to be pretty hard to read the resistivity, for instance, in one of these 2 or 3 foot zones, right? Because now I got a cloud that's what, 13 feet? And I'm going to pull out of that a 2 foot zone? I don't think so. I might want it that way, but that's not how the way that it really works. So there have always been side bed correction charts. As soon as they got to the induction phase of developing these tools, there have always been side bed correction charts that were associated with the logs. And if you haven't gone through that process, you've just missed some exciting things. It's a good way to waste your entire life trying to establish what the resistivity might be. Well, these are again things that have improved with the enhancement of computers, because now we can kind of continually make corrections, if you will, because the amount of data that we can work with to establish what the resistivity might look like to calculate with. And if you just look at those 3 points there, it's harder to tell on this slide because of the colors, but it might be easier on the sheet. The deep green dotted curve that you see, for instance, if we look at the arrow at the bottom down there at 3707 or so, you'll see the deep green curve is sliding down towards lower resistivity. It's running down towards 10 ohms, but from 20 to 10 ohms as you come up the hole. So it's not really reflecting what you would think that zone would look like to start with. It's moving in the wrong place, if you will. But if you look at the orange curve, the one that's continuously being corrected, it moves off in the other direction, right? So even though I have a consistent porosity, which we're looking at the porosity curve right here, it's not changing very much. Now I can see, if I'm going to calculate that zone, which resistivity should I be using?